So let's come back here and think about what the general structure of what we've done is. And I'll put back indices. So you can think about taking the solution that we have at the top of the board here and generalizing it to a form that would be valid at higher orders. And basically it says that the coefficient at one scale is connected to the coefficient at another scale times some evolution factor. In this case, the evolution factor is just the ratio of these alphas to a power. It could be some more complicated function at higher orders, and it could even be a matrix. That's why I've given it indices. So we could put our results back together using this higher order form so that they're generally true into our Hamiltonian and see what we've achieved. And let me call this scale that I was calling mu a minute ago mu b, just to remind you that it's a scale of order mb. So if we put the coefficient, so previously we had the coefficient and the operator at the same scale. But now using this equation, I can move the coefficient to a different scale. And so let me think of sticking this equation in. And then I have mu w. I've called mu equals mu b. So now this is mu w, mu b. So this here is the coefficient ci at mu b, but I find it useful to write it out. So the thing in square brackets is ci mu b, but I write it out using the renormalization group equation that way. And this tells you how you do the calculation. This is a fixed order calculation. This comes from anomalous dimensions and gives you the evolution. And then you have operators involving the B quark that you would calculate matrix elements of at mu b of order mb. And there's no dependence at all in those operators on the scale mw. All the mw's are in the prefactors here. You've taken that into account. You've calculated it. OK, so that's how this organizes the physics of the different scales. So you could ask, if I had this story, how would I go to higher orders? And we will have some discussion of what goes on at higher orders, because there are some things that happen at higher orders that you don't see at leading order. And they're actually important physical things. So important things to know about and keep track of if you ever want to use things like this. So let's talk a little bit about what it takes to go to higher orders. So let's just first think about what it would look like. If we went to higher orders, well, leading order was a series that I could schematically say is alpha times large logs. And I sum them all up, and I called that leading log. When I go to higher orders, I am going to continue to get series, but I get extra factors of alpha. So something that you call next to leading log, or NLL, is the same type of thing, a different series than that one, times an extra factor of alpha. So it's down compared to this by alpha s. And then you keep going. This is the general structure of the renormalization group improved perturbation theory. Just keep adding n's and keep adding alphas. Always summing up some series which changes from order to order, and that summation of that series is determined by determining higher order anomalous dimensions. So this kind of thing is called renormalization group improved. Perturbation theory. Every time you take alpha S and you take it at some scale, you're already doing renormalization group improved perturbation theory. It's just that once you have theories that have other things that run and have anomalous dimensions, then it can be more complicated than just simply picking alpha S at the appropriate scale. Here, in this theory, we have these coefficients. We have to run them, and we have to pick them at the appropriate scale, and that's what we're doing by solving these renormalization group equations. OK, so what do we need to do? We determined this. I showed you what you needed to do to get that. What would we need to do to get the next term in the series? How much would we have to compute? Well, we just have to go to one higher order in the perturbation theory. So let's make a little table. Of what it takes to get leading log, next leading log. Maybe we'll even add one more term. So there's two parts to the calculation. There's the boundary condition, and then there's the differential equation, which is the anomalous dimension. At leading log, we had tree-level matching. We determined the C plus and minus were a half. C1 and C2 were 1 and 0. And we just needed the one loop anomalous dimension. And then we just keep going in this pattern. So at next leading log, we need to match at one loop. And we would need the two loop anomalous dimension, and then et cetera. So the order in which you need the running is one higher order than what you need for the matching. That's the rule. And given those ingredients, we would be able to determine exactly these series here. OK? So there's some things that happen at this order that aren't really apparent yet at leading log. And so I want to talk a little bit about that. Before we get there, let me add one other little note. This operator O2, we didn't see it when we thought originally about matching. It had Wilson coefficient that was 0 at tree level. But so at leading order, you could say that this Wilson coefficient is 0. But at leading log, it's not 0. So in these two different types of perturbation theory, just order by order in alpha, or doing renormalization group improvement, you get different results. And that's because you've included some higher order terms by using the renormalization group improved version. But you could argue if alpha times the large log is order 1, that this is the right type of perturbation theory to do. So if you think about it as a picture, where this is mu, this is MW, this is MB, then you have two coefficients, C1 and C2. We call them C plus and C minus, but they're just related. And the results that we derived at leading order were that for C1, it started at 1 at the high scale, basically. If we take mu w equal to mw, and it would evolve actually this direction if we put in all the signs that came out of our calculations. And for C2, it starts at 0 here, and then it evolves this way to a negative value. So we can put some. So roughly putting in some numbers, kind of thing that we would get. It's this. So a coefficient which was 0 all of a sudden becomes minus 0.3 and becomes something that you have to keep track of. That's at leading log. Obviously, when you go to higher orders, those numbers will be perturbatively improved. OK? So is the physical picture here clear of what's happening with these operators?